Hello and welcome to this revision session on nuclear physics. So in today's revision session we're going to look at how we can answer examination questions for AQA A-level nuclear physics. So if we've been successful and we've learned in today's lesson, we should be able to answer A-level physics examination style questions, we should be able to assess your own understanding on A-level physics, and then finally understand what topics you need to improve upon for A-level physics. So how should you carry out this revision session? Well, when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than that on the right hand side. On the left hand section, write down your working out and answers to the questions in the revision session, and when you do this, make sure you write your answers in full sentences and show your full working out. Now on the right hand side, write down any pieces of information which you find useful or any hints and tips on answering questions from this revision session. At the end of this revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for A-level physics? So the first step is learn the key facts. Use your revision guide, your class workbooks, your student prep notes, your textbooks to learn the key ideas of the course. So you may wish to make mind maps or to write out notes yourself. The second step is to test yourself. So use the Caboodle learning platform, use the Seneca learning platform, use your own knowledge checker to quickly test your own knowledge, and you might want to do this with your own cue cards. Step 3 is then to practice exam style questions. So use the exam prep books, homework books, supervised study books, additional workbooks to help answer exam questions and mark your own work, and you may wish to download your own exam past papers to do this. So these three steps of learn the key facts, then testing yourself, and then practicing exam style questions are how you can effectively revise A-level physics. So let's have a go at a few multiple choice questions first. So uranium-238 decays by emitting alpha particles. It's not possible to influence when the decay of a particular nucleus of uranium-238 will occur. This is because radioactive decay is what? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer is B. That's because the ability not to influence the rate of decay is known as spontaneous. So from the other ones, involving high energy is irrelevant, occurring very quickly is irrelevant, and occurring randomly means you can't dictate or detail which of the radii is, or nuclei, is going to decay, only that a certain number is. Second question, which of the following is not a source of background radiation? So pause the video now, then unpause the video when you want to go through your answer. Well, the answer is C, because microwaves are non-ionizing radiation, so don't contribute to the background radiation, which is the background ionizing radiation of the Earth. Question 3. Americium is a radioisotope that decays by emitting alpha particles. The difference in mass in MeV over c squared between an americium nucleus and the products of the decay is delta M. The energy release in the decay is given by which equation? So pause the video now, then unpause the video when you want to go through your answer. Right, the answer is A, because if we say delta E is equal to delta MC squared, well, we can say that delta E is equal to delta M times by MEV over C squared times by C squared. We know that because the difference in mass we've just been told is given by the units MEV over C squared. So those C squareds cancel through, which tells us our energy release is delta M MEV. Question 4. A deuterium is an isotope of hydrogen. A nucleus of deuterium has a mass of Md. It contains one proton of mass Mp and one neutron of mass Mn. Which of the following can be used to calculate the binding energy of a deuterium nucleus? So pause the video now, then unpause the video when you want to go through your answer. Right, the answer is C, because binding energy is the change in mass over c squared, because you know that delta E is equal to mc squared, so you can work it through like that. So it's the mass of our nucleons minus the mass of the nucleus, that's our change in mass, over c squared. So when we work it through, we get our value of C, which is times c squared, not divide, sorry, times by c squared. Question 5. The graph shows how the binding energy per nucleon varies with the nucleon number for a stable nuclei. What is the approximate total binding energy for 184W? So pause the video now, then unpause the video when you want to go through your answer. Right, so the answer is D. Why is that? Well, the y-axis of our graph tells us it's the binding energy per nucleon. So what you would do is you go to 184 on your x-axis and go up and find out the value of the average binding energy per nucleon, which we see is 8. Then you go to multiply by 184, which will give us our value of 1472 MeV. That is our binding energy in MeV. Then to convert that into joules, you multiply by 1.6 times 10 to the minus 13. That gives us our answer of 2.36 times 10 to the minus 10 joules, which we want to work in picojoules, which is going to be, as you can work out, 10 to the minus 9 is then going to be 236 picojoules. So our answer is going to be D. Let's now have a look at a few longer questions on nuclear physics. So the first question is, nuclear radii can be estimated using the closest approach of an alpha particle. Nuclear radii can be determined using electron diffraction. Discuss the benefits of using electron diffraction rather than the closest approach of an alpha particle to evaluate nuclear radii. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? So it's the idea that what's our issue with using the distance of closest approach? Well, the major one is the distance depends on the alpha particle's kinetic energy, because the kinetic energy of the alpha particle turns into electrical potential energy due to repulsion between the alpha particle and the nucleus. So the alpha approach is a calculation, okay, that you're just working it out by taking your measurements, but the idea that the electron diffraction, okay, is actually a measurement you're actually working out. Now the alpha particle distance of closest approach is the maximum possible distance that it can get at before it repels. So therefore it puts an upper limit on the nuclear radius, but it doesn't actually measure that nuclear radius, because it also includes the distance between the actual alpha particle when it repels and the nucleus, as well as the nuclear radius. So our electron diffraction method actually measures the nuclear radius, while the distance of closest approach is an estimation which is an upper limit, because it also includes an extra bit of space. The next question says that show that the relationship between the nuclear radius r and the nuclear number A is given by the following equation, where ρ is the density of the nuclear material. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, the first thing you've got to do is think about how you can use your different equations to bring them all together. So the first thing to note is that the total mass of the nucleus is going to be A, which is the nuclear number, times by U, the atomic mass unit. We know our equation for the volume of a sphere is 4 over 3 pi r cubed, and we know that density is mass over volume. So we can pop in our equation for mass, AU, divided by our equation for volume, 4 over 3 pi r cubed, and then we can rearrange it to make big R the subject. So we can make that through and we get our answer as follows. Let's have a look at the next question. State what is meant by the binding energy of a nucleus, and then the possible fission of uranium-235 is represented by the following equation, and then calculate in joules the energy released in this equation. So pause the video now, then unpause the video when you want to go through your answer. Right, the first one's a very interesting one because it's just the definition you've got to learn. So the binding energy is the work that must be done to separate the nucleus into all of its separate nucleons, its neutrons and protons. Remember, even though it's called binding energy, it's the energy to separate all the nucleons. Or you can think of it as the energy released when a nucleus is formed from its constituent neutrons and protons. Now this next question, how can you work out the energy released in this reaction? So what you've got to do is as follows. You look at your particular your particular process, and you know you've got a uranium and you've got a neutron. Now a neutron actually has, you'll note, it's on the table because it doesn't have any binding energy because it's just one neutron. But afterwards you've got cesium and rubidium. So what you want to do is work out the binding energy of uranium by multiplying the value in the table by 235, because that's the binding energy per nucleon and you need the total binding energy. You'll then find the same for cesium by multiplying it by 136 and rubidium by times it by 97. Then you can find out the binding energy difference between the uranium at the start and the cesium and rubidium afterwards, and then to convert that into that's our value in MeV. Then to convert that into joules, how can we work that through then? Well, you can times by 1.6 times 10 to the minus 13 to get our answer of 2.71 times 10 to the minus 10 joules. Next question. The average energy released by the fission of a uranium-235 nucleus in a reactor core is 3.2 times 10 to the minus 11 joules. The fission of uranium-235 generates a power of 1.5 gigawatts in the core. Calculate the average mass of uranium-235 that undergoes fission in 1 second in the reactor core. So pause the video now, then unpause the video when you want to go through this answer. Right, so how do you answer this particular question? Well, you've got to understand that you want to be working out you've got to be working out the energy produced, okay, by one particular nucleus. So you can divide the power or energy per reaction. Then what you can do is convert the number of nuclei you've got into a mass. Now you can do that because you know that your molar mass is 235 grams. So at that point you can then work out what's going on in that aspect. So you can say it's 1.83 times 10 to the minus 5 kilograms per second. Now again, please do remember that power is the energy per second. So it's 1.5 gigajoules per second. So you can say that in 1 second that the total energy is 1.5 gigajoules. The energy released by one fission is 3.2 times 10 to the minus 11 joules. So you can work out how many fission events take place, and then you can work it through like that. Next question. The thermal neutrons in the core can be modelled as particles of an ideal gas. The effective temperature of this gas is 850 Kelvin. Calculate the root mean square for the thermal neutrons for this model. So pause this video now, then unpause this video when you want to go through this answer. Right, and so whilst this question is in nuclear physics and it's on the topic of fission, it's actually part of the ideal gas topic in thermal physics. So what you've got to do is, if you are given the temperature in Kelvin, you can use our following equation of a half mv squared, or half root mean squared, velocity root mean squared equals 3 over 2 kt. Why 3 over 2 kt? Because you're given the value of t and you know k is a constant. Now you know what the mass of the neutron is going to be because you can find it on the back, in the back of the equation book, and then we can equate them together and work out what CRMS squared is. You then square root it to get CRMS. So we get 4.6 times 10 to the 3 meters per second. Next question. Explain the role of the control rods in ensuring a constant power output in a nuclear reactor core. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to be able to explain how a control rod works and produces a consistent power output or a consistent fission rate in a nuclear reactor core. So the idea is that the control rod absorbs neutrons, and the depth or length at which the control rod is in the reactor vessel affects how many neutrons are absorbed, so therefore affects your fission rate. So you've got to understand that if you want a constant power output or a constant fission rate, you need 1 neutron per fission event going on to induce another fission. So the idea is that the control rod absorbs any more above 1, so it tends to either be 2 or 3 in a fission event, so the control rod will absorb them. So then you can say that because you've got a constant rate of fission, you've then got a constant power output in your nuclear reactor. The next question says that the mass of a nucleus of californium-252 is 252.03 U. Calculate the mass defect of the nucleus of californium-252. So pause the video now, then unpause the video when you want to go through your answer. Right, how do you calculate this? So the first thing you've got to notice is that you've got, in californium, you've got 98 protons and you've got 154 neutrons, because it's 252 minus 98. So that's the first mark you would get. The second mark is then trying to calculate the mass of 98 protons and 154 neutrons in U. Now again, the value of the proton and neutron in U is given in the equation book in the exam. So therefore you can work out the total, which is 254.04862 U. You can then subtract the mass of the nucleus to therefore be 252.03, so then you get the difference between the two of them, and then finally, because you're trying to work it in kilograms, you've got to convert from U into kilograms, okay, which you can work through again because the conversion factor is in the back of the equation book, so you can then use them that way, and you get your answer to be 3.3 or 3.4 times 10 to the minus 27 kilograms. The next question says the spontaneous fission of californium-252 produces a xenon nucleus, a ruthenium nucleus and 4 neutrons. Calculating MEV, the amount of energy released in this particular fission process. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you calculate the energy released in the process? Well, the first thing you've got to do is you've got to work out the difference in mass in this particular process. So the first thing you'll notice is that they don't give you the mass of the neutron, but you've got to always consider it. So please remember that this is given in the back of the equation book, and then you can use that in your calculation. So you've got your mass in U for californium, then you would work out the mass of the xenon plus the mass of the ruthenium plus the mass of the 4 neutrons, and at that point you can then find the mass difference by subtracting the mass of the xenon, ruthenium and the 4 neutrons added all together from the mass of the californium. That then gives you a value in U of your mass difference but before and after. Then you convert that into MeV by multiplying by 931.3, which is our shortcut to get our answer of our mass difference into energy release in MeV, which is 210 MeV. Next question. Some proposed fusion reactors will use a fuel of deuterium and tritium. The fusion reaction produces helium-4 and a neutron. Firstly, explain why this reaction will only occur when the fuel is at a very high temperature. Then the temperature of the fuel in one reactor is 1.2 gigakelvin. Calculate the average kinetic energy of a deuterium nucleus in the fuel, assuming the fuel behaves as an ideal gas. So pause the video now, then unpause the video when you want to go through your answer. Right, the first one is you've got to understand the conditions of the fusion process and why we have that. Well, it's the idea that the nuclei need to come within a few femtometers to fuse, because at that range the strong attractive force is then the dominant interaction, so it will pull the nuclei together to fuse them together. But they need to have a high kinetic energy, which is linked to your high temperature, because temperature is linked in direct proportion to kinetic energy, to overcome the positive repulsion of our two nuclei. Now the second question is asking the average kinetic energy of a deuterium nucleus in the fuel, assuming it behaves like an ideal gas. So what we can then do is we can say that the average kinetic energy is equal to a half mcRMS squared, which is our average kinetic energy value, equals 3 over 2 kT. So we can just say it equals 3 over 2 kT because it's an ideal gas. K is the Boltzmann constant, which is given in the equation book, and K is going to be 1.2 times 10 to the 9, because we've got to get rid of the giga there to then work out our value, and we get 2.5 times 10 to the minus 14 joules. Right, the next question says an estimate of the closest approach between the deuterium nucleus and the tritium nucleus can be made using answers. Explain how this estimation can be made. Right, so pause the video now, then unpause the video when you want to go through your answer. Right, so how can you do this? Well, how can you work out the distance of closest approach from an estimation? So what you've got to do is you've got to understand you've got your kinetic energy before, and this kinetic energy transfers into electrical potential energy when you have the distance of closest approach going on. So we can say that a half mv squared is going to be equal to q1 q2 over 4 pi epsilon 0 r. You can then rearrange this equation, make r the subject, and either have your kinetic energy as the Ke term or as a half mv squared, pop the values in and work it through. Our next question says table 2 shows the binding energy per nucleon for two nuclides involved in the fusion reaction. The energy released in this fusion reaction is 17.589 MeV. So calculate in joules the binding energy of the tritium nuclide. So pause the video now, then unpause the video when you want to go through your answer. So how would you answer this particular question? So what you've got to do is you've got to work out the two binding energies. So the idea, okay, that in this fusion process you're going to have that two hydrogens are fusing into one helium. So what you will therefore do is you'll have your two hydrogens, you add them up, you then have your helium and then add that up, then you calculate the differences to find the binding energy per, work it through, and then convert that into joules from your MeV by times by 1.6 times 10 to the minus 19. It's also worth noting that the table shows us the binding energy per nucleon. So when we need to work out the total binding energy, remember to multiply the values in the table by the nucleon number. So for hydrogen you'd multiply it by 2, and for helium you'd multiply it by 4, because the helium has 4 nucleons and the hydrogen has 2. The next question says that alpha particle comes to rest at a distance of 5.5 times 10 to the minus 14 meters from the center of a gold nucleus. Calculate the speed of the alpha particle when it's at a large distance from the nucleus, ignoring relativistic effects. So pause the video now, then unpause the video when you want to go through your answer. Again, where does this come from? It's the idea that our kinetic energy has turned into electrical potential energy. So what we can therefore do is we can therefore link the two together. So the loss of kinetic energy is equal to the gain of potential energy. So we can say a half mv squared is equal to q1 q2 over 4 pi epsilon 0 r, and then we could rearrange this all and make v the subject. Now what's very important when you do this is you recognize what q1 and q2 are. Now q1 is the charge of the alpha particle, so it's 2 times by 1.6 times 10 to the minus 19, whilst q2 is the charge of the gold nucleus, which is going to be 79 because that's the number of protons, so you can see from the question, times by 1.6 times 10 to the minus 19 coulombs, and then you can work it through like that and you get an answer of about 1.4 times 10 to the 7 meters per second. The next question says the nuclear radius of the gold nucleus is 6.98 times 10 to the minus 15 meters. Calculate the nuclear radius of silver. Then all nuclei have this approximately the same density. State one conclusion about the nucleons in a nucleus that can be deduced from this fact. So pause the video now, then unpause the video when you want to go through your answers. Right, so the first one, you've got to use our nuclear radius equation, and that is R is equal to R0 a to the power of a third. So what you need to be doing is as follows. You can either ratio the two, or I will prefer it, is you can use the information in the top line for gold to work out our value of R0, our constant. So you can say that 6.98 times 10 to the minus 15 equals R0 times by 79 to the power of a third. You can then use that to work out R0, and because R0 is a constant, you can then substitute that into our value for the silver. So you can therefore say the radius of silver is the value of R0 you've just worked out multiplied by the value of A, which is going to be 107 to the power of a third. Sorry, in the one before I should have said that the value of A is 197, not 79, because A is the number of nucleons, so it's the number of protons and neutrons. My apologies for that. So to work out our value nuclear radius for silver, it's R0, which we just calculated previously, times by 107 to the power of a third, which is 5.7 times 10 to the minus 15 meters. Now, what conclusion can you come up with the fact that all nuclei have the same density? Well, it's that the nucleons are incompressible, you can't push them in any further, or that the nucleons have a consistent separation in all nuclei, or that the idea that neutrons and protons have a similar mass and a similar volume, because as a result they can't get any closer or further apart from each other. The next question says, a thermal nuclear reactor uses enriched uranium as its fuel. This is a fuel in which the ratio of uranium-235 to uranium-238 has been artificially increased from that found in this naturally occurring ore. Describe what happens when the neutrons interact with uranium-235 and uranium-238 nuclei in a thermal nuclear reactor. So pause the video now, then unpause the video when you want to go through your answer. Well, it's very important that you know what happens when a neutron hits both of these values. So the first one is when a neutron is going to interact with the uranium-235, it will absorb the uranium-235 will absorb the neutron. It then becomes uranium-236. It will then carry out nuclear fission and then give out more neutrons. Now, when uranium-238 absorbs a neutron, it doesn't carry out fission immediately. So what will happen is it will actually gain a neutron, or it will scatter the neutron, and the uranium could become uranium-239. Then actually what happens is beta decay occurs and it becomes plutonium, and then that carries out fission later, but we're just looking at what it does when it's uranium. The next question says the amounts of uranium-238 and 235 in the ore decrease due to radioactive decay at different rates. A sample of uranium ore today contains 993 grams of uranium-238. The mass of uranium-238 in the sample was greater 2 times 10 to the 9 years ago. Firstly, show that the mass of uranium-238 in the sample at this time was about 1.4 kilograms, and that a thermal nuclear reactor requires a minimum of 3% of its uranium mass to be uranium-235. The ratio of uranium-235 to uranium-238 in the ore has changed over time. 2 times 10 to the 9 years ago, the sample had contained 52 grams of uranium-235, so deduce whether the sample had high enough uranium-235 to be used in a reactor 2 times 10 to the 9 years ago. So pause the video now, then unpause the video when you want to go through your answer. Right, so what's the first thing you've got to do? Well, in this first question, you've got to use the idea of nuclear decay. Now, the equation comes from n equals n0 e to the power minus lambda t. So what you can then do is say nt, the value of n is for the present day, and n0 is for the value being in the past. So we can therefore say that the mass of uranium is going to be 1.36 times by 0.993. So that's how much uranium-238 we've got, which is 1.35 kilograms. Now, we can then work out a half-life as well, so we could also say that we could also do it by saying the half-life is 4.5 times 10 to the 9 years. So how many half-lives have taken place? Well, it's going to be 0.44, so therefore we can say that 2 to the power of 4 over 9, or 0.44, is 1.36. So therefore we do 1.36 times by 0.993, because that's how much there is. It's 1.35 kilograms. Now for the second question, you can just ratio them. So you do your ratio of the number of 235 divided by number of 238 plus 235, and you get 3.6 to 3.7%. So therefore it can carry out nuclear fission because it's above 3%. The next question says, a thermal nuclear reactor uses a moderator to lower the kinetic energy of fast-moving neutrons. Explain why the kinetic energy of neutrons must be reduced in a thermal nuclear reactor. Then, as a result of the collision with an atom of a particular moderator, a neutron loses 63% of its kinetic energy. A neutron has an initial kinetic energy of 2 MeV. Calculate the kinetic energy of the neutron after 5 collisions. So pause the video now, then unpause the video when you want to go through your answers. So in this first one, explain why with the kinetic energy the neutrons must be reduced in a thermal nuclear reactor. Well, they've got to be travelling slower to increase the probability of fission, because it will allow the neutron to be absorbed by the uranium-235, because there need to be thermal neutrons or slow moving neutrons for them to be absorbed by the nucleus. Now the second question is actually using a bit of mathematics. It's working out that it goes down by 63% each time. Now what you can do is you can say that the final energy is going to be 1 minus 0.63 times by the incident, or 0.37 of the incident. So you can work it out each time, and you can say if it's going down by 5 times, it's going to be 0.37 to the power of 5 times by E0, because that's just a bit of mathematics working it through. I mean, you could work out 63% of the value each time for 5 particular times, or you could just do 0.37, which is 1 minus 0.63, a loss of 63%. So because it's gone down to 37%, so you do 0.37 to the power of 5 times by our starting value, which is 1.4 times 10 to the 4 eV. The next question says, one fission process which can occur in a thermal nuclear reactor is represented by this equation. Calculating MeV, the energy released in this fission process. So pause the video now, then unpause the video when you want to go through the answer. Right, so what do you do here? So you work out your mass before and you work out your mass afterwards, and don't forget your neutrons. So you work out what the mass before was, then subtract it from the mass afterwards, or vice versa, and then you find out there's a mass difference of 0.180 U. Now it's then important to note, by the way, when you're doing this particular question, because you want to work out the energy release in MeV, if you've got a mass difference in U, you multiply by 931.3 or 931.5, either is fine, to get your value in MeV. It's a quick shortcut, which is 168 MeV. The next question says, many magazines and newspaper articles focus on the risks of nuclear power. State 3 benefits of using nuclear power. So pause the video now, then unpause the video when you want to go through your answer. Well, you've got to be aware of both the advantages and disadvantages of using nuclear power. So what are advantages? Advantage number 1, there's small amounts of fossil fuels used, not no fossil fuels used. You've got to be very careful about that, because you're still going to use fossil fuels in transport and in some ways in the power station itself. So little greenhouse gas, or there's little global warming, or there's less CO2, or there's less climate change. It's very important to say that you use less fossil fuels, so there's less greenhouse gases produced, not that there's none. Secondly, because you're using less fossil fuels, the air is going to be cleaner. Thirdly, you're using small amounts of the uranium as your fuel source to get a large amount of power or energy, so the uranium has a very high energy per kilogram. Nuclear power can be produced continuously and can be very constant, while some renewables, for example, can be dependent on the conditions that you require, but nuclear is a very consistent and reliable power source. You can also have nuclear power can adjust the power output quickly by changing the depth of the control rod. And then finally, we can also produce medical isotopes in our reactor, which can be used for our benefit. Now, you can also mention the fact that nuclear fuel can be obtained from very stable countries at the minute, as opposed to oil or gas. It also can help produce nuclear weapons because you're producing those isotopes, which is useful. And also, it's the idea there's less transportation required, so there's less fossil fuels produced that way because you don't need to transfer as much fuel from power station to power station. So I hope you've enjoyed this particular revision session. So if we've been successful in this revision session, we'll be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for A-level physics. So I hope you've enjoyed this revision session on nuclear physics for AQA A-level physics. Thank you very much for watching and have a lovely day.